Chapter 3 of the Stormwater Management Guidebook covers the stormwater BMP specifications. In this video, we will discuss bioretention. The guidebook is arranged such that the specifications for each BMP type are laid out in the same format, and it includes the following subsections. Bioretention is an excellent BMP that offers multiple benefits for stormwater management as well as other co-benefits such as habitat creation and an amenity such as a landscaping feature as shown here. Bioretention is a popular practice on many sites where there's some surface land available, not a great deal needed, but some is required to install this BMP. But there are many design options and sizes that can be used to accommodate the site constraints. Looking through a few different variations of bioretentions, we have first the traditional bioretention as an example. This is what you'll see often in cities where there will generally be a defined area for the bioretention. Oftentimes there will be a hard edge defined by a sidewalk. Sometimes there will be a softer edge where there will be a slope from the adjacent turf area into the bioretention. But this is what we typically think of when we see a bioretention in an urban setting or a suburban setting. We can also see streetscape bioretention. These aren't as popular in the DC area because parking is at a premium, but there are cases where this can be an effective BMP or effective way to implement a bioretention as a BMP. Their main advantage is that they're treating highly polluted street runoff. So this is a good, if you can find space for it, a good BMP to use to treat that highly polluted runoff. Engineered tree pits are a popular use of bioretention we see in DC, where these are a tree pit adjacent to the roadway, oftentimes between that area of the pedestrian and the street access. And these are a combination of a tree pit as well as a bioretention. So using that, what would typically just be a planter area as a stormwater BMP. We also have foundation planters that you can use when you can't infiltrate. If you're using, these will be on the first floor, oftentimes over parking garages, can also be done on upper floors of a multi-level building. This is a good way of using the constricted space to your advantage and using a completely contained planter variation of the similar function of a rain garden or a bioretention, where you're getting that filtration and that temporary water capture and that retention that's achieved, but in a kind of confined footprint. Residential rain gardens are just basically the traditional rain garden, but oftentimes on a smaller scale and used more as a sort of a landscaping feature within a yard. So the feasibility criteria for bioretention, it works on a wide variety of site conditions, right? That's all soil types. You have to have some. If you're going to have an underdrain, you have to have a head available between where that underdrain is going to connect to the storm sewer. We do not recommend irrigating bioretention or putting any base flow into the bioretention, right? We want to separate the bioretention from any groundwater. We don't want any hot spots of contaminated soils or any other high pollutant loading, such as car washing facilities draining into these bioretention, because we want the bioretention to be treating polluted runoff, but not wastewater essentially. Conveyance for bioretention can be done in two ways. There's offline or an online. So if you look at this picture here, you can see, imagining this curb sloped all the way into the screen, you can see the flow would go down the gutter and then into the bioretention through this curb cut. As the ponding, as the water ponds inside of the bioretention here, the elevation of the water would rise up to the elevation of the curb cut, and then any additional runoff would just bypass. So that's an offline conveyance, and there's no overflow device inside the bioretention that's required in that case, because all of the overflow just bypasses right by the bioretention cell. If there's an online situation, so for example, there's a pipe conducting the runoff into the bioretention, or if this were in a sag position, if you imagine this is a low point and then all the runoff from both sides of these gutters are running into this point, when the elevation of the water reaches here, it's going to overflow. It's going to continue to rise and overflow out into the street, or in another case where you have a pipe conducting runoff into the bioretention and there's nowhere else for it to go, you have to convey that overflow, that excess runoff somewhere. So there has to be an overflow device. This could be a weir or an overflow riser pipe connected to a storm sewer, or an underdrain with a storm sewer connection. So there has to be some way to convey those larger storms, whether it's an offline situation or an online situation. For bioretention, since they're treating relatively large drainage areas, a pretreatment cell or some type of pretreatment is required to capture the larger sediment, the larger debris that can get into bioretention, and it helps for maintenance and maintaining the infiltration capacity of the bioretention over the long term. So that can come in a number of different forms, generally where the inlet, where the inlet pipe is discharging, or if there's a curb cut, you can put a number of different pretreatment facilities, pretreatment cell, grass filter strips if it's overland flow, stone diaphragm, any sort of pretreatment that targets the inflow of the water and removes that heavily sediment-laden flow. There are 3 different variations of the bioretention from a design perspective and from a retention calculation perspective that we have in the DC guidebook. The first is shown here, the standard bioretention design. The standard design has an underdrain. So you can see here at the bottom, there is a underdrain shown in the gravel layer. So the runoff flows into the bioretention, it ponds here at the top, it filters through the filter media down into the gravel layer and out of the underdrain. The requirements on this design is that there be at least 18 inches minimum of filter media. And because not all of the runoff that's coming into this bioretention is going to be retained, much of it is going to pass out through the underdrain. 60% of the retention value for the design storm that's captured goes towards the retention. I'll talk about that in a moment later on when we talk about the storage volume and the retention value. It's a TSS removal device, which basically means that it's filtering out the sediment. So it's can be used to treat those areas where you need the additional treatment capacity beyond the retention requirements. And it can be oversized to meet additional criteria. So if you need more detention, oftentimes you can oversize a bioretention to achieve that storage, even if it's not getting you the retention value, it can still contribute towards your detention. Now, the second variation is the enhanced bioretention with an underdrain. So in this case, there is still an underdrain, but then there's an infiltration sump below the underdrain. So on the top, you basically have the standard bioretention design, and then at the bottom, you have this additional infiltration sump. So the underdrain designs have to have a minimum of 9-inch deep infiltration sump and at least 24 inches of filter media. The storage of water that is stored down in that infiltration sump must infiltrate within 72 hours. All right, so based on the saturated hydraulic conductivity that you have for these subgrade soils, you have to be able to infiltrate that full infiltration sump volume within 72 hours. But the retention value for this design is 100% of the storage volume. And the third and final variation of the bioretention is the enhanced bioretention without an underdrain, or the full infiltration bioretention. So in this case, you only need 18 inches of filter media, and there's no underdrain at all. So the sump is basically the whole thing. The whole thing stores whatever runoff gets into the bioretention. It has to be able to infiltrate within 72 hours into the subsoil, right? So that full storage volume has to infiltrate within 72 hours. You also get 100% retention value for the storage volume of this bioretention variation. There are some design criteria related to the ponding depth. So there's a maximum of 18 inches and a minimum of 3 inches. If you have sloped sides, there must be a 3-to-1 slope, or you can have a vertical drop. So the 3-to-1 slope is meant for maintenance requirements. If you have too steep of a slope, it's going to be difficult to maintain. It's going to be difficult to grow plants and keep that vegetation on that slope. And all bioretentions must have an observation well. So this is whether there's an underdrain or not. There must be an observation well in there to be able to check what's going on in the subsurface. Is the bioretention infiltrating as it's designed? Is the underdrain clear? Is it obstructed and blocking and not allowing flow to go out of it? Or is it still clear and functioning as intended? So the observation well serves that. There's a maximum filter media depth that applies in some cases, and you'll find this by checking on table 3.20 of the guidebook. This basically looks at the runoff coefficient to the bioretention and the ratio of the BMP surface area to the BMP CDA, or the contributing drainage area, and looks at those two factors and makes sure that there is not too much filter media for the volume of runoff that's going to be infiltrating into the bioretention. So we don't want, this infinitely deep bioretention that in the design storm that it's designed for, it's just never going to percolate down and use that full media depth, right? We want media depth in there that's being utilized. So some calculations have been done and this table has been developed. So you can see here on the table 3.20 that for these high intensity storms where the bioretention is going to fill up faster than the runoff is able to filter through the media, there are situations where that lower portion of the media may not be utilized. And so by checking this table, checking what your runoff coefficient is, for example, so let's say you have a fully impervious site. So your entire CDA is impervious. So you would have 0.95 as a runoff coefficient here. And let's say you have a ratio of the BMP surface area to the contributing drainage area of 3.5%. So you would look over here and you'd look across in that row and then look down of the column for 0.95, and you'd find that you have a maximum filter media depth of 5 feet. So the modeling shows that anything past that 5 feet is essentially not going to be used in the storms, and that would be kind of wasted depth. So the maximum is set at 5 feet. So make sure to check this table when designing your bioretention to make sure you're not exceeding these maximums. Anything in the gray down here is not an issue. There's no maximum. There are specifications for the filter media, so 80 to 90% sand. It's mainly a sand media. There are some silt and clay in there, maximum 10% clay. There's also a range of 3 to 5% organic amendments and a maximum 5 and 15 milligrams per kilogram of phosphorus, depending on the test used. So these are there, the organic amendment requirements and the phosphorus concentration requirements, to make sure that there's not too much nutrient in the media itself, so that the bioretention doesn't act as a pollutant source, right? Some organic material needs to be there to establish the plants, but the idea is that the bioretention ought to be able to function as a sink, as a way of taking up the nutrients that are in the runoff, not as a source of pollution to downstream waters. Table 3.19 in the guidebook is a good summary of the filter media criteria for bioretention. So you can see there are additional requirements. You can review these on your own in the media, but just be aware of the different components of the media, the sand, the loam soil, the organic amendments, pH, salts, and the cation exchange capacity. If each of these criteria must be met and specified on the plans and met by the actual material being delivered on site. So sizing the bioretention, the storage volume is calculated using this equation here. So you can see the storage volume is a function of the surface area of the bioretention. And when we're talking here about the surface area bottom, what this means is at the bottom of ponding. So there's a surface area bottom, and then there's a surface area top. So the top refers to the top of ponding, and then that surface area average that we see over here is the average of the top surface area and bottom surface area of the ponding. So that comes into play when you have sloped sides. So if you have a sloped side, the surface area top of ponding is going to be larger than the surface area at the bottom of ponding. And then the surface area for the media and for the gravel is going to be the surface area at the bottom of ponding, right? So oftentimes this gets confused and people think, oh, bottom, that means underground at the bottom of my gravel. That should be the same area as the surface area at bottom of ponding because there's vertical sides underground, but in the ponding area you can have sloped sides, right? So to clear that confusion up, remember when you're talking about bottom here, surface area, that's the bottom of ponding. But you take that surface area and multiply it by the storage that you get in the media layer and the storage that you get in the gravel layer, right? So the depth of the media times the porosity of the media, which is 0.25, and the depth of the gravel and the porosity of the gravel, which is 0.4, gives you the storage, the sort of subsurface storage, right? The media storage and the gravel storage. Multiplying that by the surface area of bottom of ponding, and then adding that to the storage in the ponding. So this is the storage above ground. So this is taken from the surface area average, which is the average of the ponding area, times the depth of the ponding. And that's the storage volume in the ponding plus the subsurface storage here gives you the total storage. We're going to talk about a few different variations. One we mentioned earlier, we saw some examples of a tree pit, a bioretention tree pit design, and there are some additional requirements that must be met for this specific design. So if you have a tree pit, one, it has to have a tree in it, right? You have to have a tree to be able to access the stored volume that's under the sidewalk here, right? So this is for some type of structural soil or suspended pavement where the media underneath it is compacted. There are some suspended pavements, some materials where you can have the sidewalk supported without having to compact this media. But if you have a situation where the media has to be compacted, such as a sand-based structural soil, then you have to account for that porosity. Rather than having the 0.25 porosity, you have to use the 0.1 porosity in your storage volume calculations, because this volume here can count towards the storage volume as long as that 0.1 porosity is used and as long as two other criteria are met. One, that the ponding overall is an average of at least 3 inches. So you can see in this example, there's ponding out here in the tree pit, but there's no ponding underneath the sidewalk. So if, for example, the surface area of the tree pit were 100 square feet and the adjacent sidewalk and sand-based structural soil underneath it were 100 square feet as well, you would have to have 6 inches of ponding in this ponding area in order to have an average of 3 inches overall. The other item of concern in these designs is that the specifications for sand-based structural soil is not necessarily the same as for bioretention media. And the one key point that we focus on is the phosphorus content. So there must be an additional requirement on the phosphorus content. The same requirement that's on the bioretention media must be specified for the sand-based structural soil, and then it's valid. So if you meet those criteria, if you meet the criteria here, the filter media being connected to the media under the sidewalk and there being a tree there to access that, if you meet the average ponding depth overall of 3 inches, and if you meet the sand-based structural soil having that phosphorus content requirement and the porosity adjustment, then you can use that volume under the sidewalk towards your storage volume and your retention value of the bioretention tree pit. Some other considerations for bioretention, of course, the surface planting is very important. It's part of one of the key benefits of the bioretention as a BMP, but we're a bit agnostic on what that has to be, right? So you do have to have some vegetation on there, right? It can be mulch and perennial vegetation. It can be turf. It can also be stone, but there must be some perennial vegetation there, right? We want to have good vegetative coverage. It can't just be stone. That's not a bioretention. The landscaping options are critical to the bioretention function, but there are a wide variety of planting plans that can be put together and succeed. They should match the situation, right? So where the bioretention is placed, what its moisture and wetness it's going to be receiving. Consider maintenance, especially in the planting plan, and to make sure that the plants that are in that design are fit to the use and the appearance and the situation and the maintenance arrangements to ensure that they thrive long term. We also highly recommend using native plants in your designs.